So in this lecture, we will cover a more complicated scaling problem. This will be a pretty big generalization of the matrix scaling analysis that we did in lecture 2 in two directions. It'll be a generalization from diagonal matrices to arbitrary matrices, or commutative to non-commutative, and also from two parts to many parts. So that's why it's called tensor scaling. It's really strongly motivated by the next application that we have on statistics. So that the tensor scaling problem showed up like incredibly naturally with almost no transformations in the statistical application. So it's important to understand how to study optimization on these kind of problems and how to study how far the optimizer is or the balance scaling is. Cool. So first, I'll just mention this again, that we are in some sense trying to generalize the matrix scaling analysis. So like, what are the tools that we're going to need? And then I'll formalize what the tensor scaling problem is. And we'll study it using a geodesically convex formulation, which was covered a little bit previously. I'll cover it a little bit. It's just recall that convex functions were those which were convex along lines, right? So the second derivative on lines was positive. Geodesically convex functions will pick a different geometry on the space, and it'll be convex on in that geometry. And given that, we can now do an optimization perspective for tensor scaling, which is a non-commutative generalization, right? And so now we'll have the setup for what is the convex formulation for this problem. And again, when we add a strong convexity assumption, we'll again get some much stronger results, which, as I mentioned before, will be critical to the application to statistics. Cool. So yeah, we'll get started. Right, so what did we do for matrix scaling? We had a vector function. So it was a function on diagonal scalings, and it was a convex function, and we tried to optimize that function. Here we'll have more general scaling problems, and we'll have a function on positive definite matrices. That's what this is. Positive definite matrices. And so we have to pick the right geometry on positive definite matrices in order for this to make sense and to like figure out what the word convexity means. And the right geometry there is this really natural Riemannian metric. It's not important what that is, but there's a really natural set of curves that define the right geometry on positive definite matrices, right? So if you start at positive definite matrix P and you want to go in direction X, right, then it's just P to the 1/2 times the exponential curve along X. So you conjugate P to the 1/2 with E to the TX. Cool. And so like, I guess one example would be, let me do it down here. So one example, if I want to get between A and B, right, then the curve is right, so you're conjugating by A to the 1/2, and then in the inside is the direction from A to B, but not the natural Euclidean direction, but instead the exponential direction, right? So if you pick t equals 0 here, right, then you get A, and if you pick t equals 1 here, you get B. This should be worked out, and throughout you get these like geometric means. So this is a pretty well studied metric. There's a bunch of nice properties about it, but we don't need much except that this is the curve that we're going to use. Cool. But this is not enough just to have convex functions, right? Last time we needed this notion of strong convexity, and that's what gave us much faster convergence. And we needed to show that the optimizer of this problem is convex or strong convex. And there was a theorem by KLR that we used last time. So we need to generalize that for tensor scaling as well. So we're going to have to come up with some new techniques to show that if the original point is strongly convex, then the optimizer is also strongly convex. Cool. And so what is the generalized problem we're going to study? It's called tensor scaling, and we're given a tensor, right? So here's CD will break down into a bunch of parts. D1, right? Last time we were studying matrices. Matrices are two tensors, right? So there's a generalization of two tensors to M tensors, and we'll actually get a tuple of M tensors. And we're trying to do some sort of norm minimization thing again. So we define the size, which is sum of squared norms, and we want to act on this operator that we get out. So last time we were studying row and column sums of the squared entries. Here we'll study certain balance conditions on marginals of this operator. Cool. So rho of x is just the sum of outer products of the tuple of vectors, and it lives in, it's a matrix on the big space D. Right. So these are elements of C to the D, and this is D by D. Cool. And again, we're going to consider balance properties of marginals. So what are marginals? We define them with respect to the partial trace, right? So the partial trace is if you're given a tensor product, so a bunch of vector spaces, and then you're given some subset of those elements, right? Then the partial trace is just the marginal onto the part that you've asked for. So it's a matrix in DJ, right? Which is, let's say C DJ equals right. So C capital D was the tensor product of all the vector spaces. C DJ will be the tensor product of just the parts in J, right? And the marginal will again be a matrix on that space, and it will act as if on any matrix H in the same space, it's as if I acted by H times the identity on the original operator. The right way to think about this is actually just the marginals of a bunch of distributions. So like if you have a joint distribution on a bunch of variables, then the partial trace on all but let's say two of them will tell you the marginal distribution on these two. So it'll tell you the probability of showing x, y being two things as if you averaged out all the other variables. Cool. This is a unique definitions, and we'll really only consider one-dimensional and two-dimensional marginals. Cool. And so what is a tensor scaling problem is we have an operator, or we have a tuple of tensors, x, and we consider its operator rho x, right? And then we consider all the marginals, all the one-body marginals of this rho x, and we want it to be as close to the identity as possible. That's a tensor scaling problem. So we call it epsilon balanced if they're epsilon close to being the identity, properly normalized, and we call it balanced if epsilon is 0. And the tensor scaling problem is given an arbitrary tensor to scale it to be balanced. And what is the scaling? So G equals G1 to GM, right? These are, this will be act on the first space, this will act on the second space. And how do they act on the big tensor is just by diagonal. So G acts on X by G1 tensor. Right, so X is a big tensor in C to the capital D, which is a tensor product of vector spaces, and you just act by these tensor product of matrices. Cool. Note this is actually a generalization of the matrix scaling problem, right? So in the matrix scaling problem, you can consider a matrix as a two tensor with the rows and columns, and then we had left-right scaling, which is acting on the first tensor part and acting on the second tensor part. So this is again a generalization. And now we have this tensor scaling problem. It's not super clear how to solve it, but we'll just try to generalize as much as we can what we did for matrix scaling. There we are allowed to use convex optimization. Here we want to use geodesic convex optimization. So generalization to more complicated geometries, but like not that complicated, right? So we're going to introduce a convex formulation and show the same things we showed about the convex formulation that time. And then we're going to improve the analysis for strongly convex inputs. Right. So what is the convex formulation? Is this Kempf-Ness function? This is a really general theory from algebraic geometry that allows you to study orbits and like many important properties of orbits. So it's a function on not all matrices, but just positive definite matrices. I'll talk about why we can restrict to these, but the function is defined on P. So P equals P1 to PM as the size of the scaling, right? So we're again doing a norm minimization problem. So you take the point and then you scale it by the input, and then you measure the norm. We'll add this little normalization term to deal with some normalization concepts that show up later. But this is the main setup, right? So for any positive definite tuple acts naturally, and you measure the size. And why are we allowed to only think about positive definite matrices? Is because in general, our group is a bunch of matrices, but you could take the polar decomposition of that group. And if we go back to the definition of balanced, if you change it by unitaries, nothing happens, right? If you do u rho x a u star, right? Nothing changes in terms of how balanced it is. That just changes the basis. So we can just ignore all the unitary components of this problem. And that's why we're allowed to define a function just on positive definite matrices. Cool. One more simplification we'll make is the set of positive definite matrices. The geodesics that we define give you a good geometry between points, but there's actually really simple geometry from the identity to every point. And that can be captured by this e to the map, right? So the exponential map captures how to move from the identity to everywhere. And what directions can we move to stay within P, which is this tensor product of positive definite matrices, is exactly these directions, right? So if you want to keep the determinant to be 1, then, for example, you want the trace of ZA to be 0. And then that way, the determinant of e to the ZA equals x of the trace of ZA. Right. So, whoops, sorry. Right. So these are the directions that you can move from the identity that get you everywhere in the positive definite matrices. This will be helpful to figure out how to study convexity and also how to study like where the optimizer is. So like distance will be measured in this way. And our function will have a nice invariance property as well. So you can always reduce the identity just like we did in the matrix case. I'll talk about that a little more later. Cool. So this is a setup, and this is the important function that we want to study, right? And now we have a function we want to study its optimizers. We're going to show this is a convex formulation, right? So we're going to show that its optimizers are what we want to find a balanced scaling. And we're going to do that in 2 steps. So first we have to show that the critical points, or the points with gradient 0, are exactly balanced scalings. And then we show that the function is convex. So that means that global optimizers are those with gradient equals 0, right? So now how do we define gradient in the space of positive definite matrices? Is if you have Z, which is some direction that we showed right here, right? One of these directions, then the gradient is that thing which tells you the directional derivative along the appropriate curve. So the appropriate curve is e to the tz, right? So instead of just going on a line in that direction, you want to do these exponential curves. And we'll show the lemma that a scaling, it gives you a balanced tensor if and only if P is a critical point, if and only if the geodesic gradient is 0, right? So critical point means all the directions the function does not change, right? And so that we can verify really quickly. As we did last time, it's enough to verify this property at the identity by this nice little shifting trick, right? So if you have f of x evaluated at P, this is equal to f of P x evaluated at the identity, right? So it's a really simple shift from everything to the identity. And the reason you want to do that is that the geometry from the identity is quite a bit simpler, right? So it's enough to verify this property of the identity. And so now how to verify, you just take a simple derivative, right? So what is the function? This is derivative log of the size of the scaling minus the determinants, right? And this is the tensor product of a bunch of these elements. So you'll get, by the product rule, you get a bunch of you get a sum of derivatives, right? And so it'll be each partial direction will take a derivative. And then here you get the trace because you get log det of e to the tz, right? Cool. And then if you rearrange this a little bit, you can see what the gradient is, right? If you see what is the inner product with ZA, it's exactly the difference from the identity of the marginal, right? So this function is already getting close to telling us that critical points are, or how the gradient of this function tells you nice things about how close you are to balanced, right? So that's how we define the geodesic gradient. Cool. And of course, since we just took an arbitrary direction Z, if this is true, if this is 0 for every direction, then this happens only when the gradient is always 0, right? So those points where the gradient is 0 is exactly the balanced scalings. So exactly when this vanishes. Cool. So we've shown critical points are balanced scalings, and now we want to show that this function is convex in the right geometry. So convex in these exponential curves, right? And once again, we can reduce to the identity. So we'll just have to take a second derivative at the identity in every direction and show that that's non-negative. Cool. So again, we start at the identity, we take an arbitrary element C, and then we do the exponential curve in that direction, and then you take a second derivative. So this was the first derivative, right, that we calculated last time. The other term did not depend on T, so it disappears here. And this is just simple quotient rule, right? So you get a squared term for all the differences, and then you get this whole inner product squared, right? And recall that we want to show this is convex, so we want to show this thing is non-negative. And just like the matrix scaling case, this should remind you of some sort of variance term. I won't finish the calculation, but this is exactly a variance term of some probability distribution or some matrix probability distribution, right? So this is always non-negative. Cool. So we verified that the function is geodesically convex at the identity, and then by the shifting trick, that means it's geodesically convex everywhere, right? So the two things we verified is that the critical points are balanced scalings, and the function is geodesically convex everywhere. So we can just go search for minimums, and that's how you find a balanced scaling. Cool. So that gave us a strongly convex formulation for tensor scaling, and we want some strong results on the optimizer, just like we did for matrix scaling. So we're already going to introduce a strong convexity assumption. That's the next natural step, right? So what is a strongly convex tensor? Is when fx is alpha geodesically strongly convex at the identity. And what does that mean? So f is strongly convex at the identity, geodesically strongly convex, if when you look at these second derivative of these curves, that this univariate function is alpha strongly convex, right? So it's alpha times in the appropriate norm that we choose. We're going to pick this norm later, but it was strongly convex if this thing is greater than 0. It's alpha strongly convex if it curves away from the tangent line very strongly, right? And it's hard to maybe handle a tensor. Like, how do you show something is strongly convex? We can use the decomposition that we showed for the second derivative above, right? So what was the decomposition above? The second derivative is you have this diagonal term, which is from the single part marginal, and then you have this off diagonal term, right? So remember, it was sum of ZA squared, so you're going to get these off diagonal terms, and then you're going to have this extra gradient term that was above, right? So our plan is going to be to show, we're going to show that the diagonal term is large because you're close to doubly balanced. So this thing is close to the identity, this thing. Then our second step will be to use a certain important spectral condition that shows up in quantum information to show that the cross terms are small, so that this term vanishes because this thing is some sort of expander. And then also the final term will also show it's small because it's close to doubly balanced. So the gradient is already small, right? So in total, we can show that in every direction, this thing will be large. And the only part remaining is to define what the right spectral condition is to show that the cross terms disappear, right? And the spectral condition is like almost exactly what we want. This isn't really asking for much. I'm just exactly asking for the term to be small. It turns out that this really simple natural assumption that it's just a computation in linear algebra, this assumption gives you strong convexity, right? So by the plan that we showed before, you can show that the diagonal terms are large, that the gradient term is small, and then the spectral condition gives you the rest. So if, for example, lambda is like 1 over m, right? Lambda is 1 over 2m, then alpha is greater than 1 minus 2 epsilon minus. So it's some constant, right? As soon as you get that lambda is smaller than 1 over m, you get that the function is some amount of strong convex. Cool. And I'll mention this for the Pisier theorem that we're going to use later, but there's a nice interpretation of this exact condition as the quantum expansion of some quantum map. I won't go too much in detail there, but I think the right analogy is if you have, for example, a random bipartite graph, right? And then you look at the expansion of that graph, that thing will be an expander with very high probability for most reasonable random distributions. This is a very similar idea, but in quantum maps. where you can view a bipartite graph as a map from the row space to the column space, right? Cool. So now we have a definition of strong convexity, and we're going to need to show a strong convex zone around the optimizer, right, for strong convergence. And also, it's not just enough to be strongly convex at this point. In order to show anything about the function, you need some strong convexity like in a region. Otherwise, you can't really argue about the function. So how do we show that if you're strongly convex at one point, you're strongly convex at another point? In fact, the plan will be to show that each of the terms in that decomposition don't change that much. But this is the main theorem that we show in our paper on the statistical application. So if you have a strongly convex tensor and it's alpha strongly convex, right, and you scale it by some perturbation delta, then the amount that the strong convexity changes depends on the operator norm of delta. The m is kind of a weak factor, right? So as long as the operator norm of delta is much smaller than alpha, then you still get lots of strong convexity. Again, the plan was to look at each term in that decomposition and show that it doesn't change that much. Importantly, the operator norm is actually quite a bit larger, right? So most of the things we're measuring, the gradient and the distance, will be in this G norm, which is something like a 2 norm. But the robustness and convexity comes in the operator norm. So it could be that you have a very unbalanced perturbation, right? So you could have a delta that's just in one direction, delta A equals VV star, right? And then the operator norm of this thing is 1. But the 2 norm is also 1. So you have this sort of mismatch here, right? And for this reason, we're going to have to ask for a lot more strong convexity than the doubly balanced, but I'll show that later. So that's what the conditions for the main theorem are, right? So if you have some alpha strongly convex tensor, and alpha is much bigger than the error or the gradient, right? Then you have a strong convex zone that's much larger than you expect the gradient to move. Then in fact, there is a doubly balanced scaling, and that doubly balanced scaling is strongly convex because it's so close by, right? So in particular, if you move to this point, right, then e to the z star times x is cool. So by the robustness that we showed last time, when you move to this strong to the optimizer, you still have quite a bit of strong convexity because alpha squared is bigger than what's remaining. Cool. So this is the main theorem for tensor scaling that shows if you have enough strong convexity as compared to how close you are to doubly balanced, then you will have a optimizer. And the proof is quite simple. The proof is a reduction to the univariate setting. So JS convexity is just a particular geometry, but really it all boils down to univariate strong convexity, right? So we want to show that the optimizer lives in this ball. So the optimizer lives in this R ball, right? Oops. And so now what's important about this ball is that it's closed and bounded, right? So we picked a radius and then we said all the things in this norm ball. So it's closed and bounded. So there is some optimizer on the ball. There might not exist an optimizer. Generally, it might go off to infinity, but there is some optimizer in this ball. And in fact, what we're going to show is that that local optimizer is a global optimizer. And what's that going to be helpful for? So within this ball, right, we know that there's enough strong convexity for the univariate function for this direction to show that the optimizer of the univariate function is actually within the ball, right? But the optimizer of the whole ball must at least be the optimizer in its own univariate restriction, right? So it must actually be strictly in the interior of this ball. And then why is that helpful? If it's strictly in the interior, then in fact, it's a local minimum, right? If it's strictly in the interior of the ball, it's smaller than all the other points around it. And if it's a local minimum by geodesic convexity, that means the geodesic gradient is 0, right? So that means it's in fact global minimum. And the global minimum we showed are exactly the doubly balanced scalings. So if you have this much strong convexity, enough to show that every univariate restriction, the optimizer is close by, then you actually have enough strong convexity to show that the actual optimizer is close by. Cool. So this will be a useful condition that we'll use for the statistical application. So we'll need to show, if you want to show that the optimizer is strongly convex, it's enough to show that the gradient is small and the current point is very strongly convex. And that's what we'll use for the statistical application next lecture.
Great.